Next packet is the free response one. Question number 1 says an atom has 65 neutrons, so N is 65, and A mass, and you know that the atomic mass usually is identified with a capital A, so mass of 122 units. Which one is the proper nucleide symbol? So, would be some letter that we have to discover, right? 122 goes on top, and 65 is the number of neutrons. So here you should put the number of protons instead. Now you should remember that A is equal to the sum of the neutrons and protons. Therefore, by substituting our numbers, we have 122 equal to 65 plus X. Therefore, your number of protons, right? Actually, instead of X, let's write protons. I don't want you to mistake with that one, with that X. So number of protons is 57. So you check your periodic table, you see the 67 corresponds to lanthanum. So your nucleide symbol is lanthanum, and 122 goes there, and number of protons, which is 57, goes right there. So that's for question number 1. For question number 2, atom A has 11 neutrons, and atom B also has 11 neutrons. Are those atoms isotopes? No, the answer is absolutely not, because just because they have the same number of neutrons doesn't mean anything. To be isotopes, they got to have the same number of protons and eventually different neutrons. Now, if they had the same number of protons, let's say we are looking still at the lanthanum, okay? And you have a 57 for them. So if 57 is the lanthanum, you could have a mass bigger or smaller than 122 according to the number of neutrons that you have in there. In that case, those atoms will be isotopes. But to have the same number of protons and the same number of neutrons, that will mean that the atom is exactly the same kind, so they are not even isotopes, they are the same. So still the answer is no. Number 3, which component of Dalton's atomic theory reflects his understanding of the law of conservation of mass for chemical processes, and why? Well, Dalton states that in a chemical reaction, atoms are rearranged, but they are not created or destroyed. Therefore, if the atoms are just rearranged, not created, not destroyed, so mass has to be conserved. And that is why in a chemical reaction, you got to balance those atoms, right? Because let's say, for example, that you have a reaction that involves, I don't know, sodium and water, let's just say, right? And you're making sodium hydroxide and H2 gas, right? So in this case, you still have to balance your reactions. So you have sodium, you have O, you have H's, you have way too many H's on this side. So this is your products, this is your reactants, this is your products. As you notice, atoms are rearranged, but they are not created or destroyed. Looks like we're creating stuff here, but let's balance this one up. Let's see if that works, right? So you got to have, for example, 2 of those in such a way, right? You have 2 of the water molecules, which calls for 4 of the hydrogen. You have 2 here, you have 1 here, so probably you need a 2 there. And then 2 of the oxygens, which calls for the 2 here, and 2 of the sodium, which is right here. So now your atoms are displaced, rearranged, but they are not created or destroyed. So number of atoms on this side is exactly the same number of atoms on the other side, which means your mass is conserved. Number 4 says atomic masses of elements are generally not whole numbers. Explain why. Well, the reason why they are generally not whole numbers is because the atomic mass, when you look at your periodic table, you have averages there, which is, for example, if you look at the family of sodium, you have a 22.5 989,770, which means they are considering sodium with a mass of 23, sodium with a mass of 24, sodium with a mass of 21. When you average it according to the percentage, you find an average number which has to be a decimal. So that's why the decimal is there, and that is why usually you do not have whole numbers. Number 5. Gallium has two stable isotopes, gallium-69 with a mass of 68.92 and gallium-71 with a mass of 70.92 units. Using the average atomic mass of gallium, what is the percentage abundance of the heavier of those two isotopes? So how do we proceed? 68.92, that's the mass, for a percentage X. And you also have a mass of 70.92 with a mass of 100 minus X percent, which gives you the average atomic mass of gallium according to your periodic table is 69.723. 69.72, and we stop right there because they are approximating to two decimals. So for us to have 3 doesn't mean anything. And at this point you just solve, right? So you have a 68.92x plus 70.92 100 minus x equal to 79.62, whatever, 69.72. And then you have a 68.92x plus 70.92 minus 70.92x equal to 69.72. Group together, so you have a 68.92 minus 70.92. This is for x equal to 69.72 minus 70.92, and you solve for x, which is, so 60%, the minus heavier instead is going to be 40%. Question number 6. Naturally occurring chlorine is 75.78% chlorine 35, which is actually 34.9689 units, and 24.22% chlorine 37, which is really 36.9659 units. Calculate the average atomic mass. Exactly same procedure as before. 75.78% of the mass of 34.6989, and also 24.22% of the 36.9659, and this is equal to chlorine, which is 35.45. 3 and 0 because I got to match the sequence. So, and now again we solve, right? So you have the 75.78 times 34.96, this plus 24.22 times 36.9659. What are they looking for? Oh, they want us to calculate it, sorry. So this is your variable. So how much is this? And you just solve. When you solve, you will find that this is about 35, exactly 45. 30. So that's what you should find, units. Then, what conclusions were made from Rutherford gold foil experiment, and how did the experiment change the atomic model? Well, the conclusions were, remember the Rutherford experiment, it was supposed to have a detector, was supposed to have the gold foil hanging there, and So this one keeps on going, let's say like that. Then there was an emitter. So this is your emitter. This is the shooting of the alpha particles. So this is the gold foil, and this is the receiver, which is just as a screen. So when those particles got shot, sometimes they went through, sometimes they bounced back, sometimes they bounced back even more, sometimes it's just deflected. So not every single time they made it through. Now what does this mean? Well, remember the Rutherford wanted to show that J.J. Thomson was right, thinking that if this is the gold foil is made of a ton of little atoms of gold, right? Every single one of those circles, right, is gold. So this is gold, every single one of those. And when you look inside the atom, so let's isolate the atom of gold. According to Thomson, you see a ton of pluses and a ton of minuses, right? Giving the plum pudding. Now, if this was true, right, by bombarding alpha particles, which is 2 protons at the time, right, very fast, right, super accelerated, those protons, if this is if every single one of those atoms looks like this, those protons should be able to make it through, right? Should be able to just go through the gold foil, because there are tons of pluses, there are also minuses, but 2 protons going super fast in this realm of pluses and minuses should be able to make it. Just how when you shoot a gun and you have a bullet, the bullet goes through the wall because it's so fast. But that didn't happen. As you see here, those gold foils, those alpha particles were deflected. So that means the only way for those alpha particles to be deflected that much is that actually this wall that they are finding is super concentrated of stuff, right? So the only conclusion was that since this is plus and is deflected, the only conclusion is that if this is the pluses all concentrated in the center, right, when you shoot only 2 alpha particles, 2 pluses, right, those 2 pluses are not too impressive to make it through this whole barrier of plus charges. So plus and plus reject each other, repel each other. Therefore, those 2 protons are not going to be able to make it. So this is the conclusion of the gold foil, that there has to be a concentration of plus charges in the center of the atom, which we call it nucleus. And this is how the model has changed now. So you have the pluses everywhere inside, and outside instead you have only this minuses with no pluses there. So when the protons are going through the minuses are actually attracting the protons, so the protons go even faster, if you like, and they will make it through. But when those protons encounter this barrier or super entangled pluses, those 2 protons are not going to be able to make it through. Number 8, explain why the Bohr model was insufficient and how the quantum model explained the deficiency, and how is the electron viewed differently in each model. So, Bohr is stating that he agrees, obviously, because the experiments support, right, this, so he agrees that there's a nucleus there. But then he believes that there are orbits of fixed energies in which those electrons will stay, right? So here you can have electrons, here you can have electrons, right? And this vision, okay, and you should have 8 electrons, right? But this view, this is the Bohr's atom, is not, so this is the Bohr's model, it's not really corresponding to the observations, because what happens is that Bohr was playing. So first of all, the quantumization of the orbitals comes directly from the observation of those spectral lines. So when you have a line, right, shining, you will see, when you have, for example, I'm sure you have seen it in the lab, right? There's this device that contains a light bulb inside, just a tube, okay, a tube right there. And for example, let's say that this tube is shining hydrogen, right? If it is shining hydrogen, so you see the light emitted, and if you have actually a spectrometer, okay, or a spectrophotometer, you will see colors of discrete. So you will see, for example, I don't know, blue, you will see green, right? You will see orange, red. But every single one of those colors corresponds to a specific wavelength, right? You remember this. So this, for example, was 400 nanometers. This one was 780 nanometers, right? So all of those are readings that you will do with the spectrophotometer. So because there's nothing in between, this means that those electrons that are able to provide this photons, right, this much light, have to be positioned in a energy level that corresponds to the wavelength of 400 nanometers. And same thing for the red and the other colors. So because there's nothing in between, there cannot be anything in between those two circles also, because those circles are orbits of specific energies, right? So this is energy 2, for example, this is energy 1, and there's nothing in between energy 2 and 1. So this seems perfect because we can see this, right? So why is Bohr wrong? Well, it's wrong because when you actually calculate the electron volts corresponding to those particular orbits, let's say, those particular energies of the electrons for the hydrogen atoms, the electron volts do correspond to reality, but then they fail for any other atom. So that means that probably the atom doesn't look like that in reality. Therefore, the next advancement in the model of quantum mechanics is actually Heisenberg, who says that Bohr is really on task with, everything he's saying. Is just having a little difficulty there with the specific energies. So if we remove the word specific energy instead, and we leave the atom with the core, right, and we remove that one, and we have instead weird orbits, right, of clouds of electrons, then it's fine. So if you notice, what's the difference there? Well, for Bohr, you only had specific energy, for example, this one, right? But he was neglecting everything above and below, okay? So if we keep on going with the circle, we are missing all those probability places where the electrons can be. Same thing for this one. Bohr believes that it's just that particular orbit, so he's very strict with this, but he's missing this, he's missing this, so the electrons doesn't have to be here, could be here, could be here, could be here, could be around in this cloud of probabilities. So when we talk about probabilities, that's where Heisenberg comes into the game. Probability cloud. Okay. So number 9. Consider the equation relating wavelength, frequency, and energy. So energy, we know, is the H Planck, and frequency. We also know that frequency is the speed of light over wavelength, and obviously wavelength is the same as speed of light over frequency. Therefore, we can also say that energy is H, and then is C over lambda. So all of those are interchangeable. explain, so which one? Consider the equations. How is the energy of a photon related to? Well, and we just said it, so that's the game there. Next one. 10. Calculate the frequency of an X-ray that has the wavelength of 8.21 nanometers. So first of all, we got to go to meters, otherwise we cannot use the speed of light, which is the 3.0 times 10 to the 8th meters per second. So we need meters because we have meters. So the frequency is C over lambda, which means 3.0 times 10 to the 8 meters over 8.21 times 10 to the negative 9 meters. Therefore, this number is going to be 3.65 times 10 to the 16 hertz. Next one, 11. 11 says, what is the frequency of a photon? What is the frequency of a photon that has an energy of, okay, so you have the energy of, we have energy, we have frequency, I mean, so this is the equation we will use. So from here, the frequency is the same as energy over h, which means the energy they said is 3.7 times 10 to the negative 18 joules divided by the joule seconds, which is 6.626 times 10 to the negative 34. So joules and joules over, this is joules seconds. Those cancel each other out, so you're going to have as a unit 1 over second, and the number is 5.6 times 10 to the 15 hertz. And 12, please provide, they didn't say please, provide a brief explanation for what each of the four quantum number describes. So you have the number n, you have L, you have ML, and you have MS. So this one, remember, is the principal quantum number, which is the same as energy level. Then this is the azimuth, right, which is the same as the orbital. Okay, so this one can be 0, can be 1, can be 2, can be 3, which means S, P, D, and F. This one instead is the magnetic, so this is the magnetic, that's why you have the M there. Magnetic quantum number, which is the same as the orientation. Okay, and this one can be anything between minus M, 0, and M. And then we will go over those. So there's a whole series there, right? So for example, for S, you only have one orientation. For P, you have a minus 1, 0, plus 1. For D, you have a minus 2, minus 1, 0, 1, 2. For F, instead equal 3, you have a minus 3, minus 2, minus 1, 0, 1, 2, 3. And then the last one instead is the spin, right? And this one can only be plus or minus 1/2. There are no other numbers. Homework. Active americium 241 is used in household smoke detectors and in bone mineral analysis. A. Give the number of electrons, protons, and neutrons in an atom of americium 241. Write the proper nucleide symbol. Okay, so mass is 241. You see how they are, how those questions are very close to what we just said, but obviously if you understood it, you're able to answer those questions as well. So this is the mass now, right? And then they are saying americium. So that's the symbol for it. You look at your periodic table, and americium has a number of protons which is equal to 95. So this means that you will write americium 95 and 241. and they want to know give number of electrons. Well, if those are the protons, right, 41, 90, what am I saying, 95, then the electrons have to be 95 also, because they are talking about atoms. They are not talking about ions. It's just an atom, so it has to be neutral. And then how many neutrons will you have? Well, it's going to be the 241 is the mass, equal to neutrons and protons together. So this gives us a number of neutrons equal to 146. Then number 2, what characteristics do atoms of carbon 12 and 13 and 14 have in common? And in what way are different? Well, if they are carbons, right, you have a 12, you have a 13, you have a 14, but all of them have to have the same number of protons, right, which for carbon has to be 6. So as you notice, all of them are identified by the same number of protons, which identifies them as all carbons. If this was 5, then it would not have been a carbon, would have been a boron. Right? If it was 7, it would have been a nitrogen instead. But because it's 6, they are all carbons. And then, so what is changing? Well, number of neutrons here, right, is 12 is given by neutrons and protons. Here, this is for 12. For 13 is neutrons and protons, and for 14 is neutrons and protons. So as you notice, in every single one of those changes, so this is 6, this is 7, this is 8. Different number of neutrons call for a different isotope of the same element, which is the carbon. Identify the isotope that has atoms in with 117 neutrons. Okay, doesn't mean much. 77 protons, bam, right there. So which one is the 77 protons? It has to be iridium, because you read it in the periodic table. Protons are 77. The mass we don't know yet, because 77 are the protons and 117 are the neutrons. Together, those will give us the mass. And the mass is 194, which is the number that goes right there. Okay? And then the other one instead is 30 neutrons. Okay, 30 neutrons, 28 protons. This one gives us the mass, but also because those are the protons, right? The element with the protons of 28 is nickel. So you will put the nickel there, 28 are the protons, and then you add them up for a 58. And 58 is the mass of your nickel right there. And those are the two isotopes. Why are they isotopes? Well, if you read the periodic table, iridium has a mass of 192. This is a 194. And instead, nickel, this is a 58.69. This is a 58 straight. So this is the particular isotope. Number 4. How did the discovery of isotopes conflict with Dalton's atomic theory? We talked about that already. The average mass of any large number of atoms of a given element is always the same for a given element. In a large sample, the number of atoms of each isotope will match the natural distribution of abundances of each of those elements. And then number 6, naturally occurring boron is 19.9% boron 10 with a mass of whatever you see, and 80.1% with a mass of this one. Calculate the average atomic mass. And again, you do 19.9% of this mass and 80.1% of this mass, and you just do your calculation. Number 7. Uranium has an atomic mass equal to this, so you have already the number. Consists of 2 isotopes with mass and mass. Calculate the percentage. So you will take the mass times x% plus the mass times 100 minus x%, and you just solve for x. Number 8. How did Rutherford interpret the deflection of alpha particle in his gold foil experiment? Did these findings support or disprove the Planck pudding and we talked about it also. How does Bohr model of an atom explain the existence of line spectra? How are spectral lines produced? We have talked about that as well. Bohr model postulates discrete orbits where electrons can exist, specific energies. The spectral lines are created when light is emitted when electrons move from one orbit of a certain energy to another orbit of a different energy. When you absorb energy, those electrons are going up. Just like when you eat, you absorb food, so you feel a lot better. You feel, on a different, higher level of energy. You're so happy. And then all of a sudden, instead, you are dropping in energies, right? So, but you're dropping in energy because you're producing work. You're producing something. So when you're producing, you see the light. So electrons absorb energy to move to a higher level of energy. When they get tired of being at that level of energy and they drop down, releasing energy. The energy that they release is the color of what you're seeing. What is the energy of a photon? And you have wavelength. We don't know how to do the calculations. Again, is the calculation according to the energy equation. What is the energy of a photon if you have wavelength? So if you have wavelength, you got to do this, and you solve. What is the wavelength of a photon that has energy? Well, if you have this stuff, right, then you can do E over H is going to be C over lambda, but lambda at this point is going to be CH over E. So this is the final stuff. You put your numbers in there and you solve. How does the quantum number model describe the location of an electron? Again, it depends which quantum model. If it is the Heisenberg one, the electrons are in a position in a fixed energy. If it is the Heisenberg one, instead, it's just in a cloud of possible energies. So an element is found to gain 3 electrons when it forms an ion. What group number would this element be found in? And is there enough information provided to determine the period the element is in? So you have you're gaining 3 electrons. So you look at your periodic table, right? And so you have noble gases, you have the halogens, right? So those are the 8 valence electrons. Those are in the 7, so they need 1. Then you have 5, 6, whatever. So, right, and then you have 4 and 3. So if you are getting 3, 1, 2, 3, then probably they are talking about this one, okay? That in periodic table, so those are the valence numbers that I wrote down, but in your periodic table will appear as a 15. They added the 1 there, right? Obviously, because you have the 10 of the transition stuff. So 15 is the number. You can say 15 or you can say 5A. And no, you don't have enough information to decide what they are talking about. And then number 2, look at average mass for argon and potassium. To have potassium follow chlorine on the periodic table, propose 2 reasons as to why they placed argon after chlorine instead of potassium. Well, the argon is noble gas, doesn't need any other electron to complete the octet. Chlorine does need 1 extra electron. So chlorine is not happy yet. So chlorine has its own state of, so chlorine will be right here, for example, right? And then after chlorine, they have argon, right? But potassium is on the other line. So potassium is right here. So potassium instead, okay, is not happy. To be happy, we lose 1 electron to go back and be in the argon state of mind. So makes perfectly sense, right? To have the argon in this nobility place where chlorine and potassium are not. They are very close to it. Chlorine will be if he gains 1 electron. Potassium will be if he loses 1 electron. So it makes sense to have argon in between chlorine and potassium. Identify the following element. An alkali metal is in the 5th period. So identify the following. Alkali metal, 5th period. Alkali metal means you got to be here. This is the alkali metal. Fifth period, so it has to be rubidium. Then transition metal, that could be any. And then an atom in the third period that forms a stable ion with -1 charge. Third, so we're right here, -1. So that has to be the okay. Explain why atoms tend to gain or lose electrons relative to the number of valence electrons. Well, because they need to complete the octet. Explain, okay, what ions are the following elements likely to form? Nitrogen will be a nitrogen -3. Calcium will be a +2. Sulfur will be a -1. Because sulfur is, I'm sorry, -2. Sulfur is right here, so it's missing, so it's -2 electrons. So it's in negative of 2 electrons, just like in the bank, for example, you're missing $2,000 to get to the, whatever. Number 6, explain why the noble gases are inert and reactive. Well, since they have the complete valence shell, they do not need any electron to reach the state of completeness. So they are unreactive. 7. Why are the charges of transition metal D block difficult to predict? Well, they can lose 2 electrons from their outermost S orbital, but then occasionally some of the D electrons are lost also. They can create multiple types of ions. So it's weird, it's difficult to predict. Write the formula for the following binary ionic. So magnesium, and then you have oxide. So look at your periodic table. Magnesium has a +2, oxide has a 2-, so magnesium oxide is just MgO. Then manganese. So I like to write like that for myself, let's say, right? So manganese has a 2+ because they are saying so, and it's getting married with chloride, which is a -1, right? So at this point you got to balance those charges, so you need a manganese and chlorine with a 2. And then calcium phosphide, you need the calcium, which is a 2+, you need the phosphorus there, which has the 3-. So you need a calcium 3 and P2. And then you have copper, which is a 1, and sulfide, which is a -2. So you need a copper with a 2 there and S right there. Then more. Potassium sulfate. Sorry. So potassium is this one with a charge of 1. Sulfate is SO4 with a charge of 2-. So formula is K2SO4. And then aluminum phosphate. Phosphate is this. Aluminum is a 3+, this is a 3-, so that's it. They don't need anything else. And then iron 3 carbonate. Iron 3 carbonate is CO3 with a 2-, so iron 2 CO3 3 times. And then aluminum hydroxide, this is 3+, hydroxide is a -, so aluminum, and then OH, but you need 3 of those. Okay. Then aluminum reacts with a certain nonmetallic element to form a compound with the general formula aluminum 2x3. Element X must be from which group in a periodic table? Okay. So let's write what I said. So you have aluminum, you have 2 of those, X is a 3, aluminum comes with a charge of 3, so this one has to be a 2-, no questions asked. If it is a 2-, it has to be in the group of oxygen and so forth, right? So has to be the group 16, or you can say 6A. Next, homework section. What accounts for similarities or chemical properties for elements in the same group? Well, same group means technically that every single one of those elements in column, one after the other, share the same properties of having the same valence electrons. Provide the group name for the elements in group 1, which is alkali metal, 2, which is alkali earth metals, 17 are the halogens, 18 are the noble gases. Provide an example of an element in each of the above. So number 1, potassium, we just saw it before. Number 2, strontium, 17, chlorine, 18, argon. And I'm just saying you can have stuff different from me. Identify the following elements. Halogen in the in the third period. So in the third, and its halogens has to be chlorine. A metalloid. Metalloid has to be the silicon. Right? Because those, like those, right? This little ladder thing is your metalloid. You know this from last year. An atom in the fourth period that forms a stable ion with a charge +1. Atom in the fourth period that forms a stable ion with a charge +1. And that has to be potassium. Locate the following elements on the periodic table and indicate which orbital type is occupied by the valence electron. Lithium. Well, lithium is right here, right? So this one is the s orbital. So it is in level 2, so it's 2s, and you have it written right there. Silicon. So silicon has how many valence electrons? So 4, right? Because it's right here, right? Has 4. So to be 4, the P takes care of the 2 of those. The other 2 are taken care of by the s orbital. So 3s, 3p is your answer. And then copper. Copper is in the transition, right? So this is copper. So the valence is distributed between 4s2 and 3d9. What ions are the following elements likely to form oxygen? O -2, sodium +1, bromine -1. A main group element in period 4 forms the molecular compound H2E, and the ionic compound name is sodium eide, right? To which group does the element belong? And write the name and symbol for the element. Have sodium with a 2, and that's your E, right? So sodium has a charge of 1, so this one for a total charge of 2+. So on this side you got to have a 2-. You only have one of those, so you need a 2- there. And also it is in the period 4, right? So again, you look at your periodic table. Going 4, go for -2, and you find the selenium. So selenium is your element. So can you write it? Oh, yes. Okay, so the element is selenium, and the formula, if they really want to, will be this one. Then 7, write the formulas for the following binary ionic compound. So sodium has a +1, sulfide has a 2, so the formula is this. And then cobalt is a +2, chlorine has a -1, so cobalt, chlorine, and 2 of that one. Then lithium has a +1, nitrogen has a -3, so Li3 and is your formula. And then tin 4, right? Oxide at 2, so how do you balance this one up? You just write, let me find a space. So TNO with a 2 there. Okay, so this is 4 and this is 4 also. Write the formulas for the following polyatomic ion compounds. Barium nitrate. So barium has a +2, nitrate has a -1, so you need 2 of those, right? So barium nitrate, and then calcium phosphide is this one with the sugar. And then iron 2 chromate. So it stays as it is. Potassium permanganate with a charge of -1. So also this one stays as it is. And then mole concept. Answer the following question for the compound aluminum sulfate. So first of all, let's write it, aluminum sulfate. So that's a 2, that's a 3, so this is your aluminum sulfate. What is the molar mass of the compound? Well, molar mass is equal to, so you have 2 of the and 3 of the sulfur, 32.1, and 12 of the oxygen. And you add the 342. Then what is the mass? So this is for A. For B, what is the mass of 1.5 mole sample? Well, 1 mole, we have just found there is 342 grams, simply 5 moles. So 1.5 times 342 is going to be 513 grams. And then see how many oxygen atoms are present. Well, so let's go back to our number of moles. So we have 1.5 moles of the old aluminum sulfate. Okay, now in every mole of this, so follow just when you talk, right? You're just putting together the equation anyway. So in 1 mole, right, of your aluminum sulfate, okay, you have 12 moles, right, of oxygen. And also, right, in 1 mole of oxygen, you have 6.22 times 10 to the 23rd atoms of oxygen. Now you do your calculation, and you should end up with 1.08 times 10 to the 25th, 10 to the 25th atoms of oxygen. Then, what is the mass of rhodium? So 2. What is the mass of rhodium? That contains many atoms as there are in gallium atoms. So first of all, we have to find how many are those atoms, because we got to find the grams, right? But in order to find the grams, which is just a multiplication by the molar mass, which we find in the periodic table, right? So besides the last multiplication to find the grams, our job is to find the moles. So gallium atoms, they want to know how many atoms are there. So gallium atoms in 36 grams. In 36 grams of gallium, okay, 1 mole has a weight of gallium 69.72. Okay, those are the grams. So now we know how many moles of gallium are there. Okay, once we know how many moles are there, then you also know that in 1 mole of gallium, okay, there are 6.022 times 10 to the 23rd atoms. Okay, so this number is the number that we have to target. So let's reverse engineering and let's find, right? So starting from the atoms, we'll go backward until we find the grams for the rhodium instead. Okay, so okay, let's find this number first. This number is 3.11 times 10 to the 23rd. Okay, and those are atoms. So now we know how much gallium, how much atoms we want to target. So let's use this number 3.11 times 10 to the 23rd atoms, and let's say now that those are atoms of rhodium. Okay, so in 1 mole of rhodium there are 6.022 times 10 to the 23rd atoms, right? So now atoms is no more. And also in 1 mole of rhodium has a weight of 102.9. 102.9 grams. And technically we're 53.1 is the answer. Grams of rhodium. How many atoms are there in 36 grams of indium? Okay, so grams of indium, 1 mole of indium, so this is still indium. Okay, and then in 1 mole of indium there are 6.022 times 10 to the 23rd atoms. So now we know the numbers. Let's keep moving from here. Okay, so if this is the number and we want to go back to the grams, right? So our number says now we have atoms. So this is giving us atoms. We got to move to grams. So here this is basically blah 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 atoms. So there are 6.022 times 10 to the 23rd atoms, right? Of, what did I want this time? Of still rhodium. Okay, in 1 mole. And, okay, we have to still multiply here. So, so this is the mark. Okay, and in 1 mole, there's a weight of, for the rhodium, what did we say before? 102.9. 102.9 grams. Okay, so this is the part that brings us to grams again. So now those get canceled out. Those are all 1, 1, 1, whatever. Okay, so the only thing we got to do is to take the 36, right, divide by the molar mass and multiply by the new molar mass instead. Grams. Calculate the mass in grams of 0.433 moles of calcium nitrate. So first of all, the mass of this. So we got to take this one, and you know that 1 mole has a weight of, well, you got to calculate it. So you have 1 calcium, you have 2 nitrogens, and you have 6 oxygens, right? So calcium is 40. 2 nitrogens, that means 2 times 14. And this is 6 times 16. You add them up because every single one of those goes on the scale. So you have 40 plus 28 plus 6 times 16. You have a 164 grams per mole. So the per mole is here. So this is 164 grams. You see grams per mole. So this is equal to, so times 0.433, this is 71.0. And those are what was this, so grams, because this is grams, right? Then, how many formula units of calcium nitrates are present? So we cannot say molecules because this is a compound, so we talk about formula units instead. So let's go back to the 0.433 moles, okay? And in this many moles, so in 1 mole of this compound, there are 6.022 times 10 to the 23rd formula units of calcium nitrate. 433 times 6.022, 323, that is a 2.61, so 2.61 times 10 to the 23rd formula units. How many nitrates, ions, are there? Well, if you have calcium nitrate, right, and you break it up, you have calcium 2 plus and 2 nitrates. Okay, so if this is 2.61 times 10 to the 23rd, this number is still 2.61 times 10 to the 23rd, but this is twice as much, right? So this is 5.2 times 10 to the 23rd. So this is the number of ions there. Number 4, carbon has 2 isotopes, C12 and C13. How many atoms of carbon would be present in a 34-gram sample of pure diamond, which is the pure carbon? C12. How many atoms are present in 34 grams of the C12, right? So how many atoms are here? So if the mass is 12, because they are same, so, right? So 12 grams is 1 mole, okay? And in 1 mole, there are 6.022 times 10 to the 23rd atoms, right? You're done, basically. So this is 1.71, here 1.71 times 10 to the 24th atoms. Okay, and how many are instead for the 13? Well, then you do the 34 grams of carbon, but this time with a mass of 13, right? This is 1 mole, and then in 1 mole, you have 6.022 times 10 to the 23rd atoms again, right? 1.57 times 10 to the 24th atoms. Number 5, a sample of nickel, this is CO, so is hypocarbonite, right? So nickel CO is hypocarbonite. Toxic transition metal, nobody cares, has 5.23 times 10 to the 24th atoms of carbon. How many nickel does it contain? So this one has 5.23 times 10 to the 24th atoms of carbon. They want to know nickel. Well, carbon has 4, right? Because if you break this one, like just as this was math, right? For every 4 of those, you have 1/4 of nickel. So 1/4 of 5.23 times 10 to the 24th is going to be how many atoms of nickels you have. Okay. So 1.31 times 10 to the 24th atoms of nickel are present. How many grams of CO2 are there in that many liters of CO2? So how many grams? You have 7.5, 0.50, whatever liters of CO2 at STP. So because it's STP, you know that 1 mole is contained in 22.4 liters, right? So now you know how many moles are there. And then 1 mole of CO2 has a weight of. Number 7. Without doing any detailed calculations, rank the following sample in order of increasing number of atoms. Okay, so here we have, so in 0.5 moles of H2O, right, we have in 1 mole, okay, there are, so there are many, 0.022 times 10. This is just for you to see, because really you don't have to go through this whole thing. 0.5 moles of water contains that many molecules of water, right? And every 1 molecule contains 3 atoms, right? So this is the number of atoms in the water. Then instead, if you have 23 grams, right, of sodium, so 23 grams is basically 1 mole, right? Because that's the weight of it, okay? So then you have 1 mole contains 6.022 times 10 to the 23rd atoms already, right? And then for 6.0, you can say 22 times 10 to the 23rd molecules, okay? So there are that many molecules. So in 1 molecule, there are 2 atoms, okay? So just because you're looking at those stuff, right, which one has the bigger number? So those you simplify, right? So this is just 6.022. This is 6.022. This is 1/2. So this is 3/2. So this is 1.5 times this number. This is just this number. And this is this one times 2. So you have the third, the first. So it's 3, 1, and 2. So this is the order. So, and 2, and then water, and then sodium. This is the biggest, this is the smallest. They are saying increasing, so you got to move it that way, right? Smallest, and then this, and then this. This is the biggest, like we said. A reaction produces this much ammonia. So if it is ammonia produced, then it comes from nitrogen and hydrogen. You got to balance your reaction, so you need a 2 there and a 3 here. So this is your reaction, the one that will give us the ratios. Then you know that you have 0.0891 grams of ammonia. Okay, so if those are the grams of ammonia, 17 grams of ammonia are 1 mole. So this is 5.24 times 10 to the negative 3 moles. Once you know how many moles you have here, right, because this is your 5.24 times 10 to the negative 3, you think about this. So if you have 2, if you're producing 2 are coming from 1 mole of nitrogen. So you have a ratio 2 to 1. So if you have this one instead of this much, then you got to divide by 2, right? Because from 2 to go to 1, you're dividing by 2. So if instead you have this number, You got to divide this number by 2. By 2 is 2.62 moles. So 2.62 times 10 to the negative 3. But those are moles, right? So if you have 2.62 times 10 to the negative 3 moles of nitrogen, how many grams do you have? When 1 mole is 28 grams. So 0.073 grams is your number. Assuming nitrogen gas was the entire source of nitrogen and all of it was converted to ammonia, how many liters of nitrogen gas reacted, assuming the reaction was carried at STP? So it was 2.62 times 10 to the negative 3. Those are the moles. Now you know that 1 mole, okay, occupies 22.4 liters. So if you multiply the 2.62 e negative 3 times the 22.4 liters, you have a 0.059 liters. And then how many liters of ammonia were produced, assuming the reaction was carried at STP? So if it was carried at STP now, okay, let's change this one. So your moles were 5.24 e negative 3 for the ammonia. So 5.24 times 10 to the negative 3 moles of ammonia. Okay, and again, if this is gas, a normal the standard temperature and pressure, 1 mole occupies 22.4 liters. So now 5.24 e negative 3 times 22.4, 0.117 liters. Okay, number 9. Calculate the following quantities for 0.2 liters of a calcium iodide. So calcium iodide is right here. Okay, because they are asking for moles of calcium iodide, grams, and moles of I2. So let's just do it once and for all. So calcium is 2 plus and 2 iodine with a minus. So this is what the reaction, this solution looks like. Then you have calcium iodide is 0.4 molar solution, which means moles over liters. And you have and you have 0.2 liters. So how many moles do you have? 1.4 times 0.2 you gotta do, right? So 0.08 moles is what you have for the whole calcium iodide. The grams developed, well, those are the moles, right? At this point, 1 mole of calcium iodide is made by how many grams? Well, it's 40 for the calcium and 2 for the iodine. The iodine is 126.9. So all of those are grams. So 23.5 are the grams. And then moles for the I. So this is a ratio of 1 to 2. So the moles are 0. Here, let's put it here, 0.08. So this is 2 I's, so 0.16. Right, are the moles for the I2. And then 10. What is the concentration in molarity, right, of a sodium chloride solution prepared by dissolving 9.3 grams of sodium chloride in sufficient water to give? So 9.3 grams of sodium chloride. So we got to solve for moles, because molarity means moles over liters. So how many grams are making the sodium chloride? So you have 23 plus 35. So 58 grams is 1 mole. Okay. So 9.3 divided by 58. So 0.16 is how many moles you got of sodium chloride. To find molarity, right, you got to do 0.16 moles, and you have to divide this by the 0.35 liters, right? So divide by 0.35, you have a 0.46. Okay, and then number 11, how many moles of sodium ion are present in, this is easy also because you have 0.75 moles sodium phosphate. So sodium phosphate, phosphate is a 3, this is 3. So this one breaks down, oh, but we don't, what is the molarity of sodium? Yes, so 3 Na plus and PO4 3 minus. So if this, so how many moles are there? So molarity for this is 75 moles per liter, and also you have 0.15 liters. So if you multiply those two, you have 0.75 times 0.15, so you have a 0.113 moles, which means this one times 3 is going to be a 0.338 moles of sodium. And then what's the molarity of this? Well, moles per liter, so we got to divide this one by 0.15 liters. And you have a 2.25. That's the molarity of it. And we're done with the section also. Last session of homework. And then we're done. Okay, so answer the following question. You have how many grams? So you have this many grams of glucose, for which you should probably calculate the molar mass of this. So you have 6 times 12, and also you have 12, and also you have 6 times 16. So you have a 180 grams per moles for glucose. So if you need it or not, just put it aside. But I'm saying grams, so obviously I think you need it. So what's the molar mass of the compound? Bam, we've done that. How many moles are in the sample? Well, you have 3.5 grams, right? So divide this one by 180 grams per mole. So the moles are 3.5 divided by 180, which is 0.019. So if we want to make a 4 there, but 19 because this is 2 sequence. Oh no, they have 3. Okay, so 4. How many moles are there? How many hydrogen atoms are in the sample? Well, you have 0.0194 moles of the total compound, right? Now, in every mole of your total compound, you have 12 moles of the hydrogen, right? Because it says it right here. For 1 mole of this, you have 12 moles of that one. And for every mole of the hydrogen, you have 6.022 times 10 to the 23rd atoms. Okay, so those are the atoms, and it should be 1.4 times 10 to the 23rd atoms. Number 2, calculate number of moles in 1.75 grams of sodium carbonate. So sodium carbonate looks like this, for which again you got to calculate the molar mass. So 2 times 23 plus 12 plus 3 times 16. So 106 grams per mole is the molar mass, and put it aside. Now they want to know number of moles for the whole thing in 1.75 grams. So divide by 106 grams per mole, and you have the number of moles. How many formula units are there? Well, if those are the moles, right? And so this is number 2. So this is 0.0165 moles. So if this is how many moles you have for the whole sodium carbonate, they are asking how many formula units are there, which is the same as how many molecules are there, but those are not molecules. So in 1 mole, there are that many molecules, right? So those are formula units for us. So this is times 6.02 E23, and you have a 9.9 E21. And then, how many sodium ions are there? Well, in 1 formula unit, so those are how many formula units are there. They want to know how many formula units are there in the whole thing. Okay, so how many sodium ions are there? Well, if this is how many molecules you have, right, let's call it molecules. So you have 9.9 times 10 to the 21st, okay? So in every formula unit, right, so those are the formula unit. In 1 formula unit, there are 2 sodium. So this is times 2. So 1.99 E22. And those are ions. Then 3. So boron has 2 isotopes. How many atoms of B would be present in 50 grams? How many atoms of boron would be present in 50 grams of pure boron? And how many in the B10? So B11 is the one that they are inquiring first. Okay, so 50 grams, okay, of boron 11. So boron 11 means that 11 grams in 1 mole. And in 1 mole, there are 6.022 times 10 to the 23rd atoms. Whereas you redo exactly the same calculation if it was the other less pure. And then you're done. So 50 divided by 11 times 6.022 E23, there should be a 2.7 E20. The other instead is 4. A sample of this contains 0.466 moles of carbon. How many moles of hydrogens are there? We said 0.4662 moles of carbon, right? So divide by 12 and multiply by 22. So that's just a ratio, right? And this is 0.8547. Then 5, without doing any detailed calculation, well, this is just the same process that we have done before in the previous problem. And then number 6, one component of smogon is nitrogen monoxide. Car produces 8 grams of that. What is the volume? Well, 8 grams of NO. So 8 grams of nitrogen monoxide 1 mole, right? So how many moles are there? Are they asking? I lost it. What is the volume? Okay, so first of all, how many moles? And we need the moles because once we know that 1 mole occupies 22.4 liters, right? So at that point, we're done. So this is 14 plus 16. This is 30 grams. So 8 divided by 30 times 22.4. So 5.97 liters. And then a reaction, 100 grams of water. How many grams of H2 must react to produce water if 1 mole of water is produced for every mole of hydrogen that reacts? So they are saying you have H2 and you have O2, and this reacts like that, which means you need a 2 here and you need a 2 there to make everything balanced, right? So how many grams of this do you need if you want to produce grams of this? I was mixing that one. So 100 grams of this is what you have, right, what you're producing, and this is 18 grams, right? So 2 plus 16, this is 1 mole of water, okay? So 100 divided by 18, so you have a 5.56 moles of water. Okay, so how many grams of H2? So the moles have to be the same because the ratio is 1 to 1 moles. How many grams? Well, 1 mole has a weight of 2 grams, right? So this one is going to be just 11.1. So 11.1 grams is going to be your answer for that one. And then B, assuming H2 gas was the entire source of H and all was converted to water, how many liters? Well, what did we say that was? So we're producing H2, right? We need 11.1 moles were those for both, right? So we have 5.56 moles of H2, but again, we know that 1 mole occupies 22.4 liters. So that would be 124.5 liters occupied. And then, how many molecules of H2 reacted? So if those are the moles for H2, right? So 5.56 are the moles of H2, but we know that every mole contains 6.022 times 10 to the 23. This is 3.35 times 10 to the 24th molecules of H2. And then 8. Calculate the following quantities. So you have sodium sulfate in solution, and you have 1.27 molarity, so moles per liter, and you also have 0.343 liters. So this means you have 1.27 times 0.343, so you have a 0.436 moles of sodium sulfate. And then how many grams are there required to prepare the solution? Well, if those are the moles, right, let's keep going from there. One mole has a weight of, so this is 2 times 23 plus 32.1 plus 4 times 16, and all of those are grams, and those are grams. How many moles of sodium? Well, so let's not forget those were the moles that we are considering, right? The ones that we got from this multiplication. When you break this one up, you have 2 sodium plus and sulfate 2 minus. So we got to multiply this number by 2. So 0.436 times 2 is your answer, which is 0.436. 0.872 moles. And we're done with this one. 9. What's the molarity if you have KCl? You have 50 grams of this, okay, and you have 0.75 liters of that. So first of all, your 50 grams have to be converted to moles. So you have 1 mole of this is made of 35 is this, potassium is 39.1. So you have 39.1 plus 35.5, 24.6 grams. So 74.6 grams imply that you have, reverse that one times 50, you have a 0.67. And then you got to divide this one by, so you're looking for molarity, which is 0.67 moles. You got to divide by the liters, and 0.89 is the number. And then number 10, how many moles of hydroxide ions are present in? So this is what calcium hydroxide. So calcium hydroxide, how many moles of hydroxide? So we need to break this one up at some point. So let's do it right away. 2OH minus. So how many moles of this are present? And we have 0.3 liters. And you have a concentration of 2.5 moles per liter. So let's multiply those two numbers. So 0.3 times 2.5. This is 0.75. Those are the moles for the calcium hydroxide, which means you have twice as much for that side, so you have a 1.5 moles of the hydroxide. And then, what's the molarity of this? Well, once you have the moles, you divide by the 0.3, which is the liters, and you have a 5 molarity.